Okay, so for today's lesson, we're now going to look at how we can link the Poisson and the binomial. The Poisson distribution in certain situations is a good way to approximate a binomial. We started off thinking about the Poisson by looking at a situation that the binomial didn't quite fit. We had these time intervals, and for it to make sense, for there to be an individual car within each of these time intervals, we had to make them smaller and smaller. And we saw that we made them infinitely small, n became infinitely large. P became extremely small because we had so many time slots and we were only looking for the 5 cars or the 5 successes in that huge number of time slots. We're leading towards the criteria, the conditions when the Poisson is a good way to approximate the binomial. If our time intervals are infinitely small, then our p-value is also small, but our n value is large. For any binomial distribution, if n is large and p is small, then x can be approximated by a Poisson distribution. There is a rule of thumb that generally, if np, if your multiplication to find lambda, if it's less than or equal to 10, that a Poisson distribution is going to be a suitable enough approximation. In an exam, if you're asked for how you know or what the assumptions are for approximating to a Poisson, I never want you to refer to this rule of thumb. We will always mention the fact that n is large and p is small, and you'll mention those in context. P being small is really being less than 0.2. Sometimes it might be larger than 0.2, but you've been asked to do an approximation and this is the only one available to you. So you may well need to carry this out, and maybe afterwards you just comment that this may not be a great approximation. But the smaller p is and the larger n is, the better the approximation we get. Values of n that we'll say are large values of n are going to be larger than 30. Once again, you can use the np being less than or equal to 10 to gauge whether or not you're using a sensible approximation. If you haven't been asked to approximate, you don't just do it because p looked small. You would only ever do this if instructed to use an approximation. Okay, why do we want to approximate in the first place? We are transforming the binomial distribution with its 2 parameters and its probability function into a Poisson distribution with 1 parameter and quite a different probability function. Although your calculators now are extremely powerful and can probably handle the binomial in its raw form, there are some features of the binomial probability function that your calculator cannot handle. We have our NCR, we have p to the power of x, and we have q to the power of n minus x. Within the NCR, we have factorial statements. N factorial, x factorial, n minus x factorial. For large values of n, your calculator cannot handle the factorial calculation. At this point, I want you to get out your calculator and actually pause to do these calculations. Check 20 factorial. Just how big that number is. Check 50 factorial. Check 100 factorial. Your calculator won't be able to process 100 factorial. What I want you to find the first integer value that your calculator cannot find a factorial for, and tell me as you walk into the classroom. When n is large, really large, calculating n factorial is gnarly. It's difficult. It's horrible. Obviously by hand, it would be a nightmare. Even your calculator struggles. So, especially before these really powerful calculators, mathematicians didn't have much of an option but to process an approximation. So this is a bit of a legacy within the maths, the further statistics curriculum, and we need to make sure that we're familiar with the situation and the process of approximating. And when we do approximate, we eliminate the need for the n factorial, and instead we've got an exponential function which isn't anywhere near as difficult to process or compute. Okay, So a couple of examples and I'll let you get cracking with some practice. So in this first one, we're told that a call center sells magazines. The probability that a call made by the call center ends up in a sale of a magazine is 0.05. The call center telephones 100 people every hour. We could write a distribution for this. This is a binomial where n equals 100 and p equals 0.05. We've been asked to use a suitable approximation. So here it is, we've been instructed to use an approximation to find the probability that more than 10 people telephoned by the call center are going to buy the magazine in any randomly chosen hour. Okay, so we'll start with the distribution, the original distribution. So as a binomial, n is 100, p is 0.05. We know we're approximating, so let's calculate lambda. Lambda is the expectation of the binomial. That's n times p. That's 100 times 0.05. That's 5. Our lambda value is 5. Let's just do a quick check. So the three things to look for. Is n large? Yes, it is. It's 100. Bigger than 30. Is p small? Yes, it is. It's 0.05. Smaller than 0.2. Is np less than or equal to 10? np ended up being 5. We've hit all of the criteria we would look for to make sure we can approximate to the Poisson. Okay, good. Let's state the Poisson distribution. I'm going to change the notation here. The discrete random variable, let's call it y. Y follows a Poisson distribution of 5. And if we wanted to find the probability that x is greater than 10, that's approximately the same as the probability y is greater than 10. And we know to process this, it's 1 minus the probability y is less than or equal to 10. PCD, 0, 10, 5. Into your calculators, do it with me. We get 0.0137. So we started with the binomial. We saw that it fit the criteria it needed to. We calculated the expectation of x, which we know will be lambda, the parameter for the Poisson. And then we calculated the probability using that Poisson distribution. Okay, and then just one more. Here we're told that the probability of any one letter being delivered to the wrong house is 0.01. On a randomly selected day, Peter delivers 1,000 letters. Once again, this can be modeled by a binomial distribution where n is 1,000 and p is 0.01. We're instructed in the question to use a Poisson approximation. It told us which approximation to use. Using that, we should find the probability that Peter delivers at least 4 letters to the wrong house. Firstly, let's check everything fits for the approximation. N is large, P is small, N times P, is that going to be less than or equal to 10? Let's find out. The expectation of this binomial distribution is N times P, 1,000 times 0.01. I'm sure you can do this in your head. That gives us exactly 10. It fits within the rule of thumb. Let's write out the Poisson distribution. Y follows a Poisson where the parameter is 10. If you're looking for at least 4 letters with the x distribution, we would say x is greater than or equal to 4. Approximately, very closely equal to the probability that y is greater than or equal to 4. If y is greater than or equal to 4, we know for the Poisson, we rewrite that as a 1 minus into our calculator function, and we get 0.9897. It's very likely that at least 4 letters were delivered to the wrong house. Okay, so we are now moving in between the binomial and the Poisson. We're approximating the binomial when the conditions are correct to do so into a Poisson. We've seen other questions where a Poisson probability is nested inside of a binomial distribution. That's not an approximation. That's just calculating a probability appropriately, and then it incidentally is the probability we use within a binomial model. This is transforming one into the other. There is a difference. Be on the lookout for that. We'll stop there and I'll let you get on with some practice.